Okay, hello everybody and welcome to the final day of Camp 2021. It's a great pleasure to introduce Ole Warnaar, who needs no introduction because he is the President of Australia. And his talk is on some curious conjectures in Macdonald polynomial theory.
Well, I have to correct you there. I don't believe Australia has a president, but if one day they do, it certainly won't be me. But it is true that I'm the president of the Australian Mathematical Society. Anyway, so thanks everyone for showing up. And before I start my talk, I should particularly thank the organizers. I've had a very enjoyable week. Some nights a little bit late for my liking, but other than that, it's been terrific. And today I'll talk about some, I've called it curious conjectures. Curious because I really don't understand what's going on. So sometimes, of course, there's conjectures that one can make and sort of expected conjectures or conjectures that may be hard to prove. Well, I guess a conjecture is always sufficiently hard to prove, at least for the person conjecturing or stating the conjecture. But here I also don't really understand why they are there in the first place. And maybe some of you will actually have more of an idea of what's really going on. Okay, but before I get to these conjectures, I'll try to give a somewhat of an introduction into the kind of things that I'll be looking at. And so first, of course, this is about Macdonald polynomials, but I first want to take a step back and just talk about the more classical stuff, because essentially we're going to generalize this to the Macdonald polynomial setting, but not everyone may be that familiar with the kinds of things that I'm talking about. So I thought I'll first just give you a bit of the classical picture. Okay, and so I've called that vanishing integrals because that's how my collaborator Eric Rains always refers to these kind of things. So the classical setting is that of a Gelfand pair. And in case you haven't seen these kind of things, I'll just walk you through it. So essentially what we're dealing with, we have some Lie group G, and we have a suitable subgroup. So in particular needs to be compact, and then there's a few other technical conditions that need to be satisfied, but let's not worry about that. And then if we have that all the irreducible, or if an irreducible representation rho of G, if we consider now the invariant subspace or the K invariant subspace of that irreducible representation, so I'll write that as rho with a superscript K. And so we can consider that subspace and look at its dimension. And if for all irreducible representations, this dimension is at most 1, so that means it's either 0 or it's 1, then we say that G and K, they form a Gelfand pair. And there's various other definitions of a Gelfand pair, and some are the same and some are slightly different, but this is good enough for what we need here. And now an immediate consequence of this definition is that if I have a Gelfand pair GK and I integrate a character, and so this is a character of an irreducible representation of G, but I integrate that over K with respect to just a usual normalized Haar measure, then what I'll find is that either this integral will vanish or this integral may give me a 1. And that's immediately clear from sort of standard character theory, because if I take that character, so that's a character of G, and I decompose it into the, right, it's that representation, of course, is not going to be irreducible with respect to K. So if I decompose this into its irreducible components, well, the trivial representation will occur with multiplicity at most 1. If that multiplicity is 1, then the integral will give me 1. If that multiplicity is 0, then the integral will immediately give me 0. Okay, and so an integral of this type, we'll call that a vanishing integral, because most of the time the integral will just be 0. Okay, so hopefully if there's any questions about this, please interrupt me and I'll try to explain a little bit more. But that's that's the kind of integrals that we're interested in. So let's just look at an example. So if I take the general linear group here over the quaternions and take as my compact subgroup, so now I take the unitary group over the quaternions, which in fact is isomorphic. So that's what we'll see a little bit later. It's isomorphic to the compact symplectic group. Well, so what do we get? So if we integrate with respect to this compact subgroup, so here I just integrate with respect to this symplectic group, and I take a character of GLN, and as we all know, that's just a Schur function, then, well, I should get either 0 or 1, and it takes a little bit more work to actually show that you get exactly 1 if and I'll write lambda prime even. So that just means that all of the columns of that partition, if you draw it as a diagram, all of the columns have even length. Okay, so that, in other words, the conjugate of that partition is an even partition. Okay, and otherwise you get 0. So this is an example, and I think someone like Weil already knew about this integral here. Now we can make this a little bit more concrete, and that's what I'm going to do next. So, of course, by Weil's integration formula, we know that rather than integrating over the full group, you might as well integrate over a maximal torus. And of course, the price you pay for that is that in the integrand, you now pick up, in fact, the square of the corresponding Vandermonde determinant of the underlying group, and you divide your integral by the dimension of the Weil group. Okay, so if we do that, and we do that in particular to our little example here, so of course, in that case, the maximal torus, well, we can just realize this as the actual, just a n-fold complex. So this is just the n-dimensional complex torus here. And we integrate the Schur function, and pardon my notation, so this x1 plus or minus really means x1 and then x1 inverse, x2 inverse, and so on up to xn inverse. So this is a Schur function on 2n variables, right? That comes about because, of course, we were looking at the general linear group over the quaternions. So that's n by n matrices, but effectively this means that we're dealing with 2n variables here. Okay, so that's what we get. So this is, and well, then you get the square of a Vandermonde, and that's essentially the type C Vandermonde determinant that you get here. And you can rewrite that a little bit. It's not so important here. But what it says is that this integral here, so this is a very explicit integral that you could just try to compute yourself. All the pieces are very well known. It's just a Schur function and then some Vandermonde terms, and you integrate this, and well, you should get, in most cases, 0, unless the partition you start with has columns of all even length, and then you should get a 1. Okay, so as I said, this is a very concrete integral. Certainly for low values of n, you could just give it to your, well, probably first-year students, and they could try to compute this, well, provided they know what a Schur function is. It's not super difficult to do. Now, and so this remark will be important later. Let's imagine that we knew nothing about Gelfand pairs. We knew nothing about character theory. We absolutely forget everything. So we just stare at this integral and we don't know where it comes from. So we don't know.
So what happened to the squares, to the power of 2 after the equation sign?
Sorry, what happened to the squares?
Yes, the square of the Vandermonde determinant, is it still there?
Certainly here. Did I drop it in this factor here? I might have accidental. No, I think it's even. It's even here. It's this square here. So again, this notation. So I use this notation, and maybe I should have explained that a little bit more, which is very common in people working on these kind of things. So this 1 minus xi to the power plus or minus 2 means 1 minus xi squared times 1 minus xi to the power minus 2. Okay, just to make formula is a little bit more compact. And similarly with this 1 minus xi plus or minus xj plus or minus, that's 4 terms. And so you can see that that is precisely the same as, so that first term, 1 minus xi plus or minus 2, is roughly the same as xi minus xi to the power minus 1 squared, right? That's
okay,
also
true. The factors are not squared themselves.
No, these factors themselves are not squares. No.
Okay.
So this is really what you should get. And you can sort of see that this is the sort of correct, because you're essentially squaring a Vandermonde, and the Vandermonde contains, it's a product over the positive roots in the root system if you wish. But if you square, you can think essentially the number of terms should be the total number of roots in your root system. And that's precisely what you see in this second form that I've written here. I just wanted to get rid of the absolute value signs, okay? Because later in Macdonald polynomial theory, that's not very convenient to work with absolute values. So, but this, unless I made a mistake, but I don't believe so, this is really a proper equality, okay? Okay, so back to my earlier remark, let's forget about what's behind all of this. And it turns out that if you know the vanishing of the integral, so if someone tells you that if you look at this integral, that it vanishes if the partition lambda is such that not all of its columns have even length, if someone tells you that, then that implies that the integral, when the columns all have even length, so the non-vanishing case, that it would in fact equate to exactly 1. Of course, we know that it must be equate to exactly 1 for other reasons, simply because we know we're dealing with a Gelfand pair. So of course, we either get a 0 or we get a 1. So in the case when we don't get a 0, we should get a 1, right? So it's a bit silly what we're doing here, but let's imagine that you didn't know this or you forgot about that. Then the vanishing itself implies the actual evaluation, okay? So that would be a very complicated way to finding 1. So let me demonstrate how this works. And the reason I'm taking you through this little exercise is because this also works in the QT or in the Macdonald case, where we no longer have a sort of Gelfand pair mechanism behind what's going on. And then it's really sort of, that's what we need to use. So how can we see this? So, well, I'm computing a Schur function. And as I said, it's really on 2 n variables. So it's on x1 inverse, x2 inverse, ... xn inverse. Okay, so if I consider the homomorphism, so I start with a symmetric function on 2 n variables, and I write this as mapping this to the ring of symmetric, the BCN symmetric function. So that's functions that are symmetric under hyperoctahedral symmetry. Okay, so exactly a Schur function like this. So on all these plus or minuses is a function that it's not just symmetric under permutation, it's also symmetric if you replace a variable by its reciprocal. Okay, so a function like that, we'll call that BCN symmetric. And so if I consider that homomorphism from symmetric functions to BCN symmetric functions, then simply by taking the symmetric function and, as I said, evaluating this on 2 n letters with every letter occurring as well as its reciprocal, then the kernel of that homomorphism, it's spanned by differences of elementary symmetric functions. Because the elementary symmetric function EI and its elementary symmetric function that has sort of the 2 n minus I letters, they actually become the same if you take 2 n letters and they occur in pairs that are equal to 1. So you can exploit that, because that means if I take E1 times the symmetric function, or I take E2n minus 1 times the symmetric function and integrate that, and this ... that is just the same kernel here, all of the rest of that mess, then these two integrals are equal. And so now if this f becomes a sure function, I can just use the Pierre formula to actually compute an elementary symmetric function times a sure function. Okay, that's a sort of a completely standard exercise. Well, okay, I need to use slightly more. So I need to know that the normalized Haar measure, and I told you I'd forgotten about all of that, but let's say that fact is known to me. So I take that as my initial integral being 1. Then I can recursively compute the integral for all other partitions that have all columns even. So let me just do an example for you how that works. So I take two partitions, mu contained in lambda, such that they differ by only a single box. So in other words, if I take the skew shape, it would only have a single box. Okay, so well then, so I write, again, this is Eric Raines's notation. I write mu squared for a partition where you double the length of each column in the diagram. So I'll do an example in a moment. Then there is a unique partition nu that is strictly contained between mu squared and lambda squared. So let's do that. So if lambda, for example, is the partition 2,1, then lambda squared is just, as I said, I double the length of each column. So that would now be 2, 2, 1, 1. Or similarly, I repeat every row of lambda, so I let it occur twice. If I have something like that, and so now it should be clear that if mu squared compared to lambda squared, they differ by exactly 2 boxes, because mu and lambda differed only by a single box. And so there's precisely one partition that lives in between mu squared and lambda squared. And so now I apply what I said earlier, E1 times a sure function, and I take that mu is the same as E2n minus 1 times that sure function, integrated as before. But E1 times nu1, that's all ways of adding one box to a partition omega. But there's only one way to add one box such that all the columns will become even. And I know all the other ways I add a box, I will just get 0 by the vanishing condition. And so I only find a single contribution. And the same happens for the integral at the other end. I apply the Pierre rule, I get a whole bunch of a big expansion over all kinds of sure functions, but all of these sure functions will have odd length columns except for one example, which is precisely as mu squared. And so mu squared is of course smaller than lambda squared. So this way I can recursively get bigger and bigger partitions, and I always get 1. So I just do induction on the size of the partitions. So here is perhaps a more concrete example. If that was a little bit too quick, if I take the partition mu, which is a single box, and lambda has 2 boxes, then mu squared, right? I just double each column, so it just becomes the partition 1, 1. Lambda squared becomes the partition 2, 2. And so the unique partition that lives in between those becomes 2,1. And if I do an E1 times the partition 2,1, in principle, according to the Pierre rule, there's 3 ways of adding a box. But you can see that the second and the third example, they have columns that have odd length, at least some of the columns. And so they vanish by the vanishing condition. And I'm left exactly with lambda squared. And the same if I do this for E2n minus 1 times S of nu. Again, I get a whole bunch of sure functions. All of them vanish by the vanishing condition. I'm left with exactly 1 that isn't quite mu squared, but it has a complete column of length 2n. And so that complete column of length 2n doesn't contribute, because that contributes an x1 times an x1 inverse times an x2 times an x2 inverse and so on. They all cancel out. And so you can just delete that first column and you get precisely S of mu squared. And so that is sort of how you get this bigger partition 2, 2 out of 1, 1, and so on. Okay, so there's a really nice recursive mechanism that works equally well, for example, if you go to the Macdonald case. So I'll get to that later. So, okay. Well, now why should we care about such integrals? Okay, so they have a whole range of applications. And so, for example, if you have these vanishing integrals, then they're closely related to branching formulas for the classical groups. And in particular, if you're interested in branching formulas that are multiplicity free, well, once you have a vanishing integral, or once you have sort of a Gelfand pair, that will imply a corresponding branching formula without multiplicities. And that shouldn't be too surprising, because we started with a notion where the multiplicity was either 0 or 1. And so you can imagine that you can translate this into other types of multiplicity problems. And again, it tells you that the multiplicity in that other type of problem, for example, a branching problem, is either 0 or 1. So that's multiplicity free. So as I said, you can use it to find branching formulas that are sort of particularly nice. They also imply results in combinatorics. So for example, and it's not totally unrelated to what I've just said. For example, they imply non-trivial results for plane partitions. So here's another example of a Gelfand pair. So now it's GLN over the reals and just ON. And we have something, in fact, this example is sort of dual to the example that I've given you earlier. So now you see that we get vanishing unless the partition, not its columns are even, but now all the row length of the diagram of the partition must be even. So as I said, these two are sort of, this is a dual example to the one I showed you before, but you can use this particular vanishing integral to, for example, and this only takes a few lines, to show that if you compute the generating function of symmetric plane partitions contained in a box, so that's a mouthful, so if you've never seen plane partitions, so a plane partition is, so here's an example down the bottom of the page, it's just a filling of a Young diagram such that we're weakly decreasing if we move to the right or if we move down. And it fitting in a box just means that the length or the height of the Young diagram are bounded. And then it should also be the largest entry of your Young diagram or your Young tableau. Once you've put in the numbers, it should also be bounded. And symmetric just means that this picture is symmetric if I reflect it in the main diagonal. So this is a formula that was originally conjectured by McMahon in 1898, so a very long time ago. And well, as you can see, it took about 80 years for people to prove this. It was independently done by Macdonald, and you can read about that in his book. In fact, it was already in the first version of his book, the first edition, and it was also shown by Andrews by very different means. But so this was certainly considered as a complicated problem. And well, it turns out if you just use the vanishing integral, then you can give a proof of this result that takes not more than a page maybe, or maybe even less. So again, that hopefully, I mean, it's about applications, demonstrates that these vanishing integrals, they're quite powerful if you know how to use them, of course.
Sorry, may I ask a question?
Sure.
Is there a similar formula if the two first entries are different? So I mean, not N, N, M, but say N1, N2, N3.
Well, I mean, in this particular case, because this is the formula for symmetric plane partitions, and that means that, so this picture here, as you see at the bottom of the page, is symmetric under reflection in the main diagonal. So there is no point in taking these first two dimensions not to be the same, because if one exceeds the other, then you just take the minimum. Okay, so there's certainly other types of plane partitions that you can consider where you don't demand symmetry. And then, of course, you would have really an n and an m and a p, for example. You would have 3 coordinates. So, for example, if you want to enumerate plane partitions that fit in a box without symmetry, there's also a really nice formula for that. Then it depends on 3 rather than on 2 variables. Incidentally, that formula is much easier to prove. So of all of the plane partition formulas, or for plane partitions confined in a box, this was by far the hardest to actually prove. And it's not a priori clear that that should be the case, but that's just how it is. Okay.
What's the difference between the numerator and the denominator and the second factor? They look exactly the same.
Oh, well, that m should not be in the denominator. I apologize. That is, yes, that is not a great, that is not good. That's just a mistake. Thanks very much. That should not be there. Yes, sometimes you write in just writing, it's no, that's that of course makes no sense, right? Because that second factor would just be 1. That is certainly not what it should be. My apologies. So thanks for pointing that out. Okay, so in any case, so hopefully I've convinced you that these vanishing integrals, they're of some interest and they're useful also in applications in various fields. Okay. So, well, of course, given that this is about Macdonald polynomials, we really have to lift everything we've done so far from Schur to Macdonald. Okay. And so in this case, so previously we were dealing with the square of a Vandermonde, and it was essentially the first example that I gave you was the example where, well, this Gelfand pair, where we essentially had the complex symplectic group. So we have something of type Cn. And so the role of that square of the type C Vandermonde is now going to be played by what I call the Koornwinder density. So it's a complicated function, and the precise details are not so important. It depends on quite a few variables. So those of you who know about Koornwinder polynomials, they know that they have quite a lot of variables, sometimes called A, B, C, and D, and I'll call them T0, T1, T2, and T3. There's also a Q and a T, and so on. And in any case, it's some complicated density. And what's the relation to Koornwinder polynomials? Well, for those of you who know what a Koornwinder polynomial is, if you integrate 2 Koornwinder polynomials with respect to this density, and the first one you take it with the alphabet x, and the second integral you take the reciprocal of that alphabet, then, right, you get 0 unless lambda, the 2 labeling partitions of these polynomials are the same. So this is sort of the orthogonality of Koornwinder polynomials. Okay, so this is sort of a QT deformation of the square of the Vandermonde determinant of type C. All right, and so, okay, so let's just move on from that. And then there's a second thing, so we still use the terminology Koornwinder, and so this is called a virtual Koornwinder integral. And so what we're going to do is simply take a symmetric function, and so this is some functional, we just take a symmetric function, like we did with that Schur function, we evaluate that function at x plus or minus. So really what you should read here is x1, x1 inverse, x2, x2 inverse, dot, 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 xn, xn inverse. And we integrate this with respect to this Koornwinder density. And to make sure that if we integrate just the function 1, that this thing normalizes to 1, sort of to have something that is analogous to the normalized Haar measure, I just divide this by the integral where you don't have that function f. Okay, so this now has the proper normalization. So this thing here is called, for any function f, we call this the virtual Koornwinder integral. Okay, and so these are, if you wish.
So does the denominator have a nice product form?
Yes, the denominator, absolutely, of course, because the squared norm. So again, for those who know about Koornwinder polynomials, I only gave you the 0 here, but the squared norm of the Koornwinder polynomials is very nice. Just like in the Macdonald case, you get things that are very nice. So that's true, but it would just be some complicated formula that I would have to write down. But it's absolutely true that this denominator is an explicit evaluation that I think it was first computed by Gustafsson a long time ago. Not in the context of Koornwinder polynomials, before Koornwinder polynomials were even discovered. But that's right. Okay, so this is going to be essentially our analog of the type. So let me just go back of integrals of this particular form. Okay, so rather than just a sure function, we can put any symmetric function we like, and instead of the square of the type C Vandermonde, we have this Koornwinder density. And it's normalized in exactly the same way as here, so that if we integrate 1, we just get 1. Okay, so this is now our QT analog. So there it is again. And well, question is, can we find some good functions f such that we get nice integral evaluations? Well, of course, we know that if we take in the classical case, if we integrate the sure function, that was the example we did earlier, we got something that is nice. And it was first conjectured by Eric Rains and then later proved by Rains and Vazirani that indeed, if you just replace the sure function by the Macdonald polynomial, well, you need to tune your Koornwinder parameters correctly. So again, this plus or minus t to the power 1/2 just means plus t to the power 1/2 for the first one. The second variable is minus t to the power 1/2 and so on. So this is really 4 of these Koornwinder variables. Then this integral gives you 0, the same as before, unless your partition lambda is of the form mu squared. So in other words, if there is a partition mu such that if you square mu, so in other words, if you double all the length of each column, that gives you your lambda. And they also obtained a really nice, we no longer get 1, but in the case when there's no vanishing, so your partition has even column lengths, then there's a very nice explicit formula in terms of these arms and leg lengths of your partition. Okay, again, the precise details are not that important, but it's certainly a pretty evaluation. And you can see that if Q is equal to T, which brings you back to the classical world, then the numerator, so in this case, the numerators and denominators fortunately are not the same, but when Q is equal to T, they do become the same, and this just becomes a 1. Okay, so this is a QT deformation of 1 as a really nice rational function that can be expressed sort of in terms of combinatorial data related to the partition. So you really take the product over all squares inside your partition, and then you compute for each square the arm, the leg, and the co-leg and the co-arm length, and you stick it into this, and that's the evaluation of your integral. So it's quite an amazing result, I think. If you've not seen this before, certainly the first time I saw this, I thought, well, that's really quite special. Okay. All right. Well, so it turns out, so I'm not going to give you the full proof of this thing. Obviously, we can no longer rely on just having a Gelfand pair, and we don't really have a notion of a QT analog of a Gelfand pair. That would be nice that we could just get this for free, but that's certainly not the case. So the evaluation itself, as in the sure case, the evaluation follows from the vanishing. So now you see the evaluation is no longer a trivial one. You get this nice combinatorial product over all the squares of your partition. So you might wonder, how do you ever get this? Well, you get this simply from the vanishing. The vanishing, and again, just the Pierre formula for Macdonald polynomials. So now the Pierre coefficients for if you take the multiplication with the elementary symmetric functions is no longer either 0 or 1, but it is again something that is really nicely factorized. So this psi prime function, I'm not stating what it is, you can look it up in Macdonald's book, but again, it has a very combinatorial flavor. And now if you do exactly the same exercise, this recursive exercise that I did over here, you get exactly the same. The only thing is that the coefficients in this recursion now become these Pierre coefficients, but they are combinatorial. And if you iterate those, then you can precisely obtain, or you will precisely obtain this product here over all these arms and legs. So that's where it comes from. So this really is determined by the Pierre formula for Macdonald polynomials. Of course, what it doesn't do for you is give you the vanishing part of this statement. So for the vanishing part, you have to work quite a bit harder. And essentially what you do is you need to use the, well, I'll call it the BCN, because that's what Rains and Vazirani call it, the BCN affineheka algebra. And it's somewhat non-trivial, because what you need to do is that sort of, you need to first go non-symmetric. So you need to deform this Koornwinder density to something that is a non-symmetric Koornwinder density. But if in any case, if you do this in the right way, so that also means that you, okay, so, well, here I said a little bit, I don't think it's that important, but if you just wonder where these Koornwinder parameters show up in this BCN affineheka algebra, well, so of course you have the usual braid relations, and then you have some quadratic relations, and they contain these variables t0 up to t3. Okay, again, the precise details are not that important, but if you consider a non-symmetric analog of this virtual Koornwinder integral, and again, for the sake of time, I won't write it down, but Rains and Vazirani did, then this combines really, really nicely with the action of this affineheka algebra. So in particular, if you take this non-symmetric Koornwinder integral and you take one of these Hecke generators, then, well, in either what it does, it just pulls out a factor of t, and this L here should not have been an L, that should have been an I. And this same L here on the right, that should also have been an I. So my apologies. So this should have been an I tilde on the left and an I tilde on the right. So it's another little typo here. And so that happens if the generator is T0 or Tn. And for all the other generators, you again see something going on that we saw earlier with this Pierre business, that you get a relation between something that's indexed by I and indexed by 2n minus I. And without giving you the rest of the details, but we saw earlier on that there was a really nice interplay between I and 2n minus I. And again, if you do all the details, that's precisely enough in this particular case to actually show the vanishing. Okay, so as I said, the vanishing, you have to work a little bit harder, but you just use affineheka algebra techniques. But in spirit, it's not that different to showing the non-vanishing case. So, okay, so in any case, I'll leave out the details. So this is well understood. So before I get to the conjectures, again, why should you care other than that? I think just a result like this is very pretty in its own right. Okay, but if you want actual applications, again, there's plenty of applications. So for example, these vanishing integrals, they give rise to actual character formulas, but now for affine Lie algebras. Okay, it's not that surprising that when we deform things rather than in the classical world, we now are in the world of affine Lie algebras. And so, for example, for affine type C, you can, here's a particular example. So I take some irreducible representation of Cn, and well, this is just a very special one. So lambda 0, that's just the zero fundamental weight, and I take a multiple of that. So I look at the character of that particular irreducible representation, and you can express this in terms of a modified whole Littlewood polynomials. So we've seen modified whole Littlewood polynomials earlier in the week. So they're just obtained from the ordinary whole Littlewood polynomials by some platistic substitution. I've written that here down the page. And of course, well, you need to explain what t and the xi's, what they really are in terms of your root data. So t, I should maybe have used q here, but of course the whole Littlewood polynomials, we usually use a t. This is really the t of whole Littlewood, but it's actually e to the power minus the null root or the imaginary root. And then the xi, again, they're sort of e to the some linear combination of the other simple roots in the affine root system. Okay, so this follows, well, not, I shouldn't say directly, you have to do quite a bit of work, but ultimately you can prove a result like this using these vanishing integrals.
I'm sorry, and how does the parameter m enters the right hand side?
So that's missing. So it's lambda prime is even, and there's also a condition on the largest part of this partition that should be bound, I believe, by 2m or by m.
Oh, I see.
Yeah, that's you're a sharp observer here. I think in my later example it's actually included, but you're quite right, it's missing on this page. I'll make sure I correct these little things. So here on the next page you see a very similar formula, and now you see indeed there is a bound on the largest part of the partition, which also should have been included in that earlier formula. So you don't just get character formulas, but you can also get these Rogers-Ramanujan type identities, which is a topic I'm very interested in, again, related to affine Lie algebras. And again, if I take the example of affine type C, then you can show that if you sum these whole Littlewood polynomials, where you evaluate them at sort of these progression, so 1, q squared, and so on. So this nice geometric progression, infinitely many variables. And so you get a nice infinite product. Okay, the notation here, these theta, they are just Jacobi theta functions. So again, this is something that you can get out of these vanishing integrals. You get these higher rank Rogers-Ramanujan identities. You can also get the actual Rogers-Ramanujan identities as a sort of very special case. Okay, so again, so these Qt analogs of these vanishing integrals, they're pretty in their own right, but they have applications to mainly representation theory and Q series and so on. So well, in view of the time, I better move on. So now some conjectures. So first, some sort of general statement. So the condition that lambda prime, so in other words, all the column lengths of a partition have to be even, or all the row lengths of a partition have to be even. That's quite common in Macdonald polynomial theory. Okay, so we already saw it in these two vanishing integrals just for the sure case, where we saw conditions either lambda prime even or lambda even. But what, at least as far as I'm aware, is much less common is where you sort of have a mix, where in fact you have the condition that the 2 core of the partition must be 0. So for those who are not familiar with cores in general, well, we only need a 2 core. So a partition has empty 2 core. It just means that you can essentially tile it with dominoes. Okay, so here I've given you a partition that has empty 2 core because you can tile it with dominoes. Okay, that's good enough for us here. There's of course the more general notion of a P core, and a lot of you will know what that is, but we won't really need that. Okay, so note that a partition that is even, so all the row length even, or all the column length even, they certainly are examples of partitions that have an empty P core, because you can always tile those partitions. So this is sort of a weaker condition. Okay, and as far as I am aware, this hasn't sort of occurred in Macdonald theory a lot. So here, well, recently with Chul-hee and Eric, we observed that there's a large number of results that hold for with either this condition where partitions must be even or the conjugate of the partition must be even, that there is analogs of these results where now you have the condition that the two core of the partition must be empty. And so here's the first conjecture. Again, I take this virtual Koornwinder integral and I have these four Koornwinder parameters and I take them to be, well, pairwise, so plus a to the half and then minus a to the half, and the same with the next two parameters. This integral vanishes. At least that's what we believe. Not just that, but if in the non-vanishing case, so if the two core is actually empty, then again, you get a nice evaluation in terms of arms and legs and co-arms and co-legs of the partition. And the formula is a little bit more complicated. So there's a q to some power and a t to some power in front, and I didn't bother to write it down. It's probably a good thing given the number of typos I've already made here. And so there's this, and then it continues on. Okay. And there's a second example of such a nice evaluation, again, in terms of arms and legs. And it's very mysterious to us what's going on here. We can't use these sort of general Heka algebra techniques to prove the vanishing. We also can't use Pierre techniques that if we assume the vanishing to get these evaluations, because we really do not recognize. So previously I told you that in the one example I gave you from Rains and Vazirani, you could sort of understand these coefficients that you were getting because they essentially came from the Pierre rule. Okay, so if you would be very observant, you would have noticed that some of these coefficients were essentially coming from Pierre. But here, right, we get these strange conditions that either the co-leg and the co-arm, they must be, the sum of them must be even. And similarly, in the bottom, it must be odd. So note that when q is equal to t, this thing is not going to cancel. It's not going to give us a 1 because we're taking a product evens in the numerator, odds in the denominator, and something similar in the second product. So where do these products come from? We have no idea. And as I said, there's a second example. I just write something similar. It's, again, a big formula, but it's, again, completely factored nicely over these arms and legs. And again, there's a lot of even and oddness going on. And once we found this, we realized that there's many other formulas, some of them related, but some of them completely unrelated, where something similar occurs as well. So in any place where in Macdonald theory, there's a result about even partitions or about partitions with even columns, you can find a corresponding result where it is now with empty two cores. So I've just, okay, so here this remark, before I give you more examples, this page is just to point out that these empty two cores is no longer so nicely behaved with respect to the Pierre rule. And so because you get many partitions contributing, if you do this sort of similar kind of idea where you hope that you can set up some recursion on the size of partitions with empty two core, you can try a similar technique, but unfortunately you get many, many terms on the left and you get many, many terms on the right. And so, and then all these terms, they evaluate with these really complicated evaluations over evens and odd boxes, and it's combinatorially, it becomes a complete mess, and it's totally unclear why these recursions hold. And we certainly can't prove them. We can't even show that they completely determine the evaluation in the first place. So we're really at a loss here. But in any case, that's just to indicate that we have no idea how to prove things. But here is another example. So these types of identities are known as Littlewood identities. And again, there's examples of this already in Macdonald's book, where rather than T2 core being 0, it is either even partitions or partitions with even column length. Here we have examples of that with this empty two cores. And again, you see this even and oddness going on. But on the right-hand side, you get a beautiful infinite product. Okay, so again, these are pretty formulas. This conjecture is actually not unrelated to the previous one that I've shown you. But it doesn't stop there, right? Here's another conjecture related to some branching formula, which really, we have no connection between this one and the previous conjectures. So now what I do is I take a Macdonald polynomial, index it by some rectangular box, so a partition of rectangular shape. Again, I evaluate it at sort of 2n variables. So this first x should, of course, have been an x1, and then an x2 plus or minus 1, dot, 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 and so on. And you can expand this in terms of Macdonald polynomials, and I use old-fashioned Macdonald notation rather than affine root systems to label these. So I apologize for that. But in any case, you can try to compute the branching coefficients here. And I haven't explicitly written them down for you. But notice that again, we get the condition that these coefficients are 0 unless the 2 core of my partition is empty. And if the 2 core is empty, there's some function f. I haven't written it down for you, but again, it's completely factorized in terms of arms and legs. And again, there's an even oddness going on. Very, very similar, but we don't know how this conjecture relates to any of the previous conjectures. And there's other results like that. So that, for example, we found a BCN version of, well, this is if you know about hypergeometric functions, of something that is known as Andrew's Q analog of Watson's 3F2 summation. So that's a mouthful. And again, I'm not giving you the details, but the structure of the sum is there's some really nice hypergeometric term. You sum over it. And again, that thing is going to be 0 unless the 2 core of your partition is empty. And in that case, it evaluates nicely into some other function that I haven't given you. Again, it's completely factorized in terms of these arms and legs and so on. And it just keeps going on. So it really seems something is going on. And that's sort of where I'll stop. And it's really a question, I guess, for the audience, because we're at a lot, what is going on? So what is behind all of these conjectures? As I said, not all of them are related, but there's certainly a number of them that appear to be completely unconnected. And as I already indicated earlier, the usual affine-heka algebra techniques seem to break down. And there's also another technique that was developed by Eric Rains to deal with some of these vanishing problems using elliptic interpolation methods. Unfortunately, they also seem to fail. So whatever is out there at the moment can deal with these kind of empty 2-core conjectures. And so we have pretty formulas, but we have very, very little understanding of what is really going on. And I probably should stop there. So thanks very much.
Thank you. Very nice talk. Any questions?
Yeah, Ole, I have a question.
Yes.
Can you go back to the conjecture 3?
Sorry, number 3?
Yeah, here. So does it have a nice Hollywood degeneration? So Q goes to 0.
The Q goes to 0 case here is in fact known. So because what happens, I mean, as you can see in this formula here, there's Q to some power and then T to some power. And they're a little bit complicated to express what these powers are, again, because of even and oddness conditions. But you can imagine that when you set Q equal to 0, you get additional vanishing.
Yes.
And because of that additional vanishing, this 2 core being empty, of course, in fact, you get a stronger vanishing condition and you get one of the classical vanishing conditions.
Okay. Yeah.
So that case, but it is also true that the other limit, so this is the Q to 0 limit, that one is known, but the T to 0 limit is not known. So, but yeah, the Q to 0 limit is gives you something for whole Littlewoods that's just a standard. And I can't remember if this one is that the partition has to be even. It probably is the one where the column length of lambda have to be even.
Okay. And I guess Q equals T is also very easy to prove.
Not really. So even Q equal to T is new. You can then use Pfaffian methods. And in fact, Seamus Albion, who is here in the audience as well, he is currently working this out. So the Q is equal to T case can be proved, but is surprisingly was not known. So some of these Littlewood identities, right, they go all the way back to Littlewood, quite a few of them, certainly for sort of type B and C and D, sort of the classical, for the classical groups. But this one is new, even in the Q is equal to T case. So that's very surprising.
Okay, thank you.
Yeah.
Can I ask a question? So this 2 core being 0 seems, I mean, there is one instance I know of it, and I was wondering if you know such a thing. So if you take a sure function and you evaluate it in the variables x1 through xn and minus x1 through minus xn, then that factors, I mean, that is 0 unless the 2 core is empty. And if it isn't, then you get a factorization in terms of sure functions of the 2 quotients. So this is a result of Dipendra Prasad from 2016. So I know that it's not the same thing, but I'm wondering if somehow.
It's certain. So that I'm not sure if I know that particular result. It's certainly true that in the sure case, there are, which is exactly the reason also why we understand the Q is equal to T case a little bit better, because also these sort of Pfaffian methods essentially imply the same thing. You get the vanishing. And so there's some other sure results indeed where these empty 2 cores have shown up, even in some of Eric's work. And so I'm not sure. So if you could send me a reference to that paper, that would be great. But okay, certainly in sure case, there is probably what you're referring to is the same thing that we know about. So yes, the sure case is definitely easier. One can do something there, but we don't know what's going on in the Macdonald case.
So yeah, so my question, so I posted the link in the chat.
Okay, great, thanks.
But my question was, because you seem to find this whole family of things, yes. Is there, underlying this whole business, is there a way to maybe, is there something that takes the x inverses to minus x's somehow? Is that what's going, I mean, because here
inverses to minus x's.
That's the result. That's what I'm saying.
Well, because he's using rather than the reciprocals, you're saying.
Exactly.
Okay. Right. Okay, well, I would have to look at that particular result first then, because that's a little bit different from what I have.
Yes,
it doesn't immediately ring a bell, but yeah. Anyway, thanks for pointing that out. It's something for me to look at. I'm not sure if it's going to help in the Macdonald case, but anyway, understanding even the sure case better might be useful. That's
yeah. Okay. Thanks.
Can I ask you to elaborate on your comment that the affine seem to fail? What does that?
Well, seem to. I mean, so maybe that's not the correct thing to be saying. The point is that the combinatoric. So this. So let's just go back to the first conjecture, which is just the vanishing integral. So you can do exactly the same as what Rains and Vazirani did, right? You can consider the sort of non-symmetric analog of this. And it's still true that the Heka algebra, sort of the action of the Heka generators on this non-symmetric version of this Koornwinder integral, it acts really nicely. Okay, so you get exactly the same relation types of relations that I wrote here, except for, as I said, there were some typos. These L's on the right should also have been an I tilde. So these kind of things are they still hold. But now the question is, can you use these results to infer the vanishing, right? So does it give you enough combinatorial information that you can really understand what is going on? So in the case of this first example of Rains and Vazirani, it's relatively easy to do that, because having a description that all the parts of your partition must be even, or a description that all the column length must be even, that's relatively simple. And there's some symmetry going on. And as I said, in particular, the fact that the Heka generator Ti, you can relate that to the action of T2n minus I. That's really, really helpful and useful. We don't really know what that does on partitions with MT2 core. It just, as I said, combinatorially things just blow up and it's completely unclear. So obviously, well, if one is clever enough, you could say, well, things should still work. But to even just starting to set up the combinatorics, it just looks like a total mess. And dealing with these MT2 cores, and as I said, similar with the Pierre reaction, we just, yeah, you just get very complicated equations that really seem very dependent on your partition, right? Somehow you can do this uniform. So in the range Vazirani case, it's enough to know that your partition has odd column length. Then, for example, in the Pierre rule, these recursions you get, regardless of which partition you take, you always get one term on the left and one term on the right, right? So that's a very easy structure, and that's very easy to solve or to even check that you, right? We already have the solution that's conjectured. You just check, you stick it in and you see that it works. Now, if you do this with these MT2 core partitions, it's very dependent on the partition. So for some MT2 cores, you may get 6 terms on the left and 25 on the right. And for another partition, you might get a different number. And so, right, it just becomes a completely, it's a nightmare. So in that sense, it's just, we don't know how to use the affine-Heka algebra or Pierre or other techniques, simply because the combinatorics looks like hopeless.
Okay.
But there must
All
be
right.
some underlying principle, obviously. There's something about these MT2 cores that say that these things work. But any particular example that I do, I can check, or my computer can check it for me. But, right?
Right.
Yeah,
All right,
yeah.
great,
So
thanks.
that's not a very satisfactory answer. I understand, but so it's maybe not. It's not the Heka algebra's fault. It's the combinatorics, but there should be something deeper that explains that. Oh, the combinatorics may look difficult, but actually, right? It's not so bad. Another way of looking at this that where one can see what's really going on, and we just don't know what that is.
Okay, great, thanks.
Well, I have a question. Did anyone study Young's lattice of this MT2 course? Because one can always add dominoes so that
you can always add dominoes. Yeah, that's sort of what we sort of naively tried, right? That's sort of what you see in this. Well, where is that?
Yeah.
Sort of, that's right. You can always, that's right. You can always get one by removing a domino, right? That's essentially how you, of course, in general, if you want to find the 2 core, whether it's empty or not, right? That's how you do it. You remove ribbons or strips of length p, right? If you're talking about p core. So that's generally how this is done. And of course, we know there's many ways of removing these things, but it doesn't matter. You always end up with the same p core and so on. But I don't think here that the Young's lattice that it would really help. Again, it would probably look very, very complicated, right? I mean, probably a better description would be using sort of Littlewood's decomposition, which is probably better than the combinatorial picture, because that immediately explains, for example, why it doesn't matter which way you remove the remove the dominoes, right? Or the abacus model or whatever, but still it doesn't seem to help us here very much.
Okay, then I have another question. There are also transformations of integrals. Can they be also understood in terms of vanishing?
Transformation. I'm not sure really what you're referring to.
Like Gustafson's integrals, there are transformations also of
Yeah, but
different
that's
dimensions.
that's somewhat different, right? There's many integrals and integral transformations in all of maths, but here we're talking about these vanishing integrals. There are very specific types of. I'm not sure if there is, and I'm not sure that would be interesting, right? It's really the cool thing is that you mostly get zeros here, and if you don't get a zero, you get a very nice factorized form. I think as soon as you let that go, then what's the point, right?
Yeah, well, you might have a transformation.
You might have a
Extending.
transformation, but remember, I mean, you might be interested in these things just for their own sake, but we're really interested in these things because, right, they imply branching formulas, character formulas, Rogers Ramanujan identities, identities for plane partitions, whatever it is. As soon as you make things too complicated, then all the applications go out of the window, and it's just it becomes much, much less interesting, I think. So, yeah, I'm not sure that's worth really investigating at all.
Okay. Then I would have one more question. In the Koornwinder case, they extend the Askew-Wilson polynomials, correct? And if you let t equals t, but leave the other parameters, t0 to t3, what you get, can you know?
Sorry, if you do what?
Q equals t in the Koornwinder polynomial case.
Yes.
For n equals 1, do you know which set of orthogonal polynomials you have?
Oh, I mean, yes, we do. I mean, in general, we know exactly. So there's typically 3 points that are really, really special. And so there's these two related to sort of symmetry. So between type B and type C, that's sort of these traditional vanishing integrals that we've known about for a long time. And essentially what we're sitting where we find all this two-core stuff is precisely in the middle at self-dual points. Referring to the involution on the the omega qt of Macdonald polynomials, that involution on the ring of symmetric functions. Now, if you go back to Askew-Wilson, yeah, it's not one of these sort of special. I mean, that's the whole point, that this particular case is not natural from the point of view of orthogonal polynomials. So it doesn't have a special name, for example.
Okay,
Can I ask, so one more conceptual question, Ole. Is it fair to say that these vanishing integrals are to Littlewood identities what orthogonality is to Cauchy identities?
Yes, that is absolutely right. So as I said, not all these things are unrelated. Any vanishing integral you have, you immediately get a Littlewood identity out of it. And essentially you use duality for that. And it's precisely sort of the Pierre type, or not the Pierre, the Cauchy. So it's precisely what you're thinking, yes.
Okay, thank you.
Yeah.
Okay, any further questions? If not, perhaps we can thank the speaker again. Please unmute yourself.